In this video, we will study about parallel adder with accumulator. Before to that, let us know what is an adder accumulator. An adder is a digital circuit that performs addition of numbers. There are two kinds of adders, half adder and full adder. Half adder is a combinational logic circuit which performs the addition of 2-bit binary input and produces two output in the form of sum and carry. Full adder is a combinational logic circuit which performs addition of 3-bit binary input and produces output in the form of sum and carry. Here, combinational logic circuit means the output is dependent on only the present inputs. This is the truth table of full adder. As we know, full adder has 3 inputs in the form of A, B, and C and produces 2 outputs, sum and carry. These are the equations of sum and carry. Sum is equals to A XOR B XOR C. Carry is equals to A XOR B into C plus A into B. Triple carry adder. It is a binary adder used to add 2 n-bit numbers. It is called triple carry adder because the carry at every stage is rippled to its forward stage. So it is called triple carry adder. Let us take an example by taking 4-bit triple carry adder. A is 10 and B is 12. By adding these two numbers, we have to get sum as 12. These are the inputs to A and B. At the initial stage, let us take C in is equals to 0. By adding 0, 0, 0, we will get sum as 0 with carry 0. Here carry is 0 and sum also 0. In a similar way, by adding 1, 1, 0, we will get sum 0 with carry 1. By adding 0, 0, 1, we will get sum 1 with carry 0. And by adding 1, 0, 0, we will get sum 1 with carry 0. So finally, the output produced is 1, 1, 0, 0. It is equals to 12. So we got output as 12. The main difference between the triple carry adder and the parallel adder with accumulator is here we don't store the output produced in the accumulator. In the parallel adder with accumulator, we will store the output in the accumulator. Accumulator is made up of flip-flops. A flip-flop is an electric circuit with 2 stable states that can be used to store binary data. Types of flip-flop: SR flip-flop, JK flip-flop, T flip-flop, and D flip-flop. Accumulator register is basically made up of D flip-flop. A D flip-flop is a digital electronic circuit used to delay the change of state of its output signal until the next rising edge of clock signal input occurs. This is the truth table of D flip-flop. Why it is used to delay the change of state means if we provide clock as 0 and even though if we provide D input as 1, it will not change the state of the flip-flop until we provide clock 1. It will be retaining its state. So it is called D flip-flop. D flip-flop is called data flip-flop. Parallel adder with accumulator. It is nothing but storing one number in the register of flip-flop and adding a second number to it, leaving the result to be stored in the accumulator. This is the circuit diagram of n-bit parallel adder with accumulator. It is an iterative structure made up of similar cells and each cell containing one flip-flop and one accumulator. Let us know the inputs of the flip-flops and accumulator. The flip-flop having 3 inputs, which one is add signal, clock signal, and clearance signal. Here clearance signal is an active low input. Means if we provide clearance signal as 0, it will reset the flip-flop. And add signal is connected to the clock enable of the flip-flop. It means if without providing the add signal, even though we applied the clock, it will not change the state of the flip-flop. If clock enable is 0, it will disable the clock. The input for full adder is one come from the flip-flop, another is the external input given to the adder and carry from its previous state. Let us know how two numbers are added in the n-bit parallel adder with accumulator. First, let us assume one number is already stored in the flip-flops and another number is given as input to the full adder. By the time carry is propagated through all the flip-flops, the sum is available at the output of each flip-flop. If we provide add signal equals 1 and at the rising edge of the clock, the sum will be stored back in the flip-flops. Here, suppose the number x is equals to x and 2 x1 is stored in the accumulator. Then the number y is equals to yn to yn is applied to the full adder inputs, and after carry is propagated through the adders, the sum of x and y appears at the adder's output. An add signal AD is used to load the adder output into the accumulator flip-flops on the rising edge of the clock. Suppose if the present state of flip-flop is 0 and sum produced by this full adder is 1, the next stage of flip-flop will become 1. Next stage of flip-flop means if we provide one clock signal by having D input as 1, the D flip-flop will change state from 0 to 1. That is called next stage of the flip-flop. If the sum produced by full adder is 0, then the next stage of flip-flop will be 0. In the general case, if Si equals to 1, then the next stage of flip-flop is Xi will be 1. If Xi equals to 0, then next stage of flip-flop Xi will be 0. That Xi plus means next stage of the flip-flop will be equals to Xi, and if add signal equals to 1, the number X in the accumulator is replaced with the sum of X and Y following the rising edge of the clock cycle. Before addition can take place, the accumulator must be loaded with value X. This can be accomplished in several ways. The earliest way is to first clear the accumulator using asynchronous clear inputs on the flip-flop and then put X data on Y inputs to the adder and add to the accumulator in the normal way. This means first we have to clear the all data what is there in the flip-flops by using clearance signal. If we provide clearance signal equals to 0, it will reset all the flip-flops to 0, and we will provide the X value to the Y inputs and we add 0 to it. By adding any number with 0, we will get the same number, and by providing one clock signal, the X value will be stored in the flip-flops. We can store the number in another way. Alternately, we could add an multiplexer. Alternately, we could add multiplexer at the accumulator input so that we could select either Y input or data output loaded into the accumulator. This is the multiplexer, which is 2:1 multiplexer, and load signal is used to select whether we have to give Y input to the flip-flop or some input to the flip-flop. If we provide load equals to 1, then it will select Y input and it will provide D input as Y. And if load equals to 0, it will select some of the flip-flop. The accumulator flip-flop can either loaded with directly from yi or from the sum of the full adder. When load input is equals to 1, the multiplexer select yi and yi will be loaded into the accumulator flip-flop on the rising edge of the clock. When add equals to 1 and load equals to 0, adder output Si is loaded with Xi. The add and load signals are R2 together to enable clock when either addition or loading occurs. When both add and load equals to 0, the clock is disabled and accumulator output will not change. Let us take an example and discuss how it 3-bit parallel adder with accumulator work. Initially, we have loaded all flip-flops with one value which is equals to 4, and we provide 2 to the y inputs. 2 equals to 0 1 0 and 3 and 4 equals to 1 0 0. By adding 0 0 0, we will get sum as 0 with carry 0. By adding 0 0 1, we will get sum 1 and carry 0. By adding 1 0 0, we will get sum 1 with carry 0. So we have got sum as 1 1 0, which is equals to 6. When we provide one clock signal with add equals to 1, the accumulator flip-flop will store the value 6. This is how the 3-bit parallel adder with accumulator works. Applications of parallel adder with accumulator are PCD to XS1 code converters. Parallel adder with accumulator is also used in ALU for heavy computing environment. They are used in analysis of multiplication algorithms.